All right, this is a ranking of the acids. This is the Chem 4 supplement. And so this supplement has some additional information here. Here we have hydronium. Hydronium is at the border between strong acids, which are above here, and weak acids, which are below. The weak acids are ranked in order of strength. And so the strongest of the weak acids that are shown here is trichloroacetic acid. This H was supposed to be tacked on to the back of the COOH here. This is kind of weird because it looks like a peroxide. Do you know anything about peroxide bonds? They're really weak, yeah. But it's not a peroxide, it's just the way that traditionally it's been written. It has a little different structural unit. But anyway, trichloroacetic acid is one of the strongest of the weak acids. And then we have oxalic, chlorous, and then hydrogen sulfate or bisulfate, phosphoric, nitrous, hydrofluoric, formic. This is hydrogen oxalate or bioxalate, acetic acid, carbonic acid. Carbonic acid has this little asterisk here. Carbonic acid is not very stable. It decomposes into water and CO2. And so that's why there's an asterisk there for carbonic. Hydrosulfuric acid or hydrogen sulfide, dihydrogen phosphate, hydrochlorous, ammonium, hydrocyanic acid, boric acid, bicarbonate or hydrogen carbonate. And this is hydrogen phosphate or monohydrogen phosphate, so that there's no confusion. And then we have a borderline water, and then we get these acids down here. These acids are so weak. They're weaker than water. And water is really not considered an acid. Water is considered kind of neutral, but it can act as an acid. But these would be weaker than water. It would be ammonia, hydrogen. Hydrogen we don't normally think of as an acid. Hydrogen sulfide ion, hydroxide ion. Hydroxide is a strong base. And so on the flip side of this, we have what we call the bases. And this is called a conjugate relationship. So if hydroxide loses an H+, then it forms the conjugate base oxide. And so these are conjugate pairs, which we call them. And we can go back and forth from the conjugate pairs. So if we take oxide and gain an H+, we form hydroxide. And so it's just back and forth depending on if we lose. So for example, HS minus, if it loses an H+, it forms S2 minus. If S2 minus gains an H+, it forms HS minus. And so this conjugate pair, the reason we want to know about the conjugate pairs is because there's a conjugate relationship. The conjugate relationship goes like this. If hydroxide is a very, very weak acid, in fact, it's too weak to be a Bronsted. I call it Bronsted for short, but it's really technically Bronsted-Lowry. If it's too weak to be a Bronsted acid in water, B species, then it doesn't want to let go of this H+. In fact, it doesn't want to donate the proton. It wants to hold on to it. And so what that means is oxide has a powerful affinity for proton. That is, it wants a proton, and once it gets it, then it holds on to it. And so if the acid is weak, its conjugate is strong. And so oxide is a very powerful base because it really wants a proton, an H+. Whereas if we go up here, if the acid is very strong, then it loses its proton very easily. Strong acids need to lose their proton easily. That means its conjugate, which is perchlorate here, so this is the acid, its conjugate perchlorate must be weak. It must not really want a proton all that much. In fact, these bases here are too weak to be Bronsted bases in water. Then they really don't want to pluck a proton off water. We'll talk about that more.
When do we use bases and when do we use acids?
Depends on what's given in the problem. And so we look at the species that are given and then just analyze it based on where it is on the chart. And so when we use it, is depends. We're gonna use it, but it depends on what they give us. So if they give us oxide, not hydroxide, then we're gonna use oxide here. Then we're on the base. Some of these species occur on both sides of the chart. So for example, HS minus occurs on both sides, so it can go either way. Things that can go either way are called amphoteric, but when I say go either way, that is, HS minus can act as an acid. If HS minus acts as an acid, it loses a proton. Over here. Let's see if I can. So it forms sulfide, but HS minus can also gain a proton, but if it gains a proton, it forms hydrosulfuric acid, H2S. So yeah, it can go either way, but which direction it goes will form a different thing. So for example, hydroxide can act as an acid to form oxide, its conjugate base, or hydroxide can act as a base and form water if it gains a proton. So hydroxide gains a proton, it forms water. So we have this. Hydroxide, it turns out hydroxide is the strongest base that can exist in water. All these other bases are too powerful to exist in water. And so these are extremely powerful bases here. I should write that.
And so memorize this?
No, you don't have to memorize these.
I mean, it's going by a pattern to figure out where it is.
Yeah. So let's take, it's going by the pattern. You have to memorize the 7 common strong acids, but not really. I mean, those are typically given. So let's go back over here. I'm going to insert this in the PowerPoint. Here. I'm going to name this acids. These are Bronsted, Lowry, acids and bases. Bronsted, they're two different people, but they're both given credit for this, so we hyphenate the name here. Bronsted and Lowry, acids and bases. It turns out that hydronium ion is the strongest acid that can exist in water. And so that's highlighted here. The strongest acid that can exist in water. What the implication of that is if I have any of these acids, they don't exist in water. That is, they completely ionize or completely hydrolyze in water. We call it hydrolysis because the water actually reacts here. And so this is our acid, this is our base, and what we see is it's going to form hydronium and nitrate. And so we don't find any minor species like nitric acid molecules. It's all dissociated 100%. The other way of writing this is as an electrolyte. That is, nitric acid doesn't exist in water, it dissociates into the ions. And so this one equation we call hydrolysis. Lysis is just breaking apart of water, but it's the reaction with water here, hydrolysis. This is our acid, this is our base. So this is an acid-base reaction here. Over here we're kind of looking at it as an electrolyte. You know, HNO3 is a strong electrolyte. And what do strong electrolytes do? They dissociate or ionize in water. And so when we look at over here, it breaks up completely into ions. But what do you know about the proton ion? Is the proton ion all that stable? No, it's not. It's very reactive. And it's going to react with what? Protons like to react with what? They like to react with water to form hydronium. So when we do the proton here, I probably should put a little asterisk. This is quite reactive. And the protons are quite unstable. What makes them so unstable? Does anybody remember? What I said about the stability of the proton? Stability, like compared to other +1 cations. They're too unstable to exist in water. Nobody remembers why they're too unstable to exist in water? Not at all. Has to do with their size.
Maybe they're so small that their charge, what's it called? Their force, the law here, is small.
Yeah, so I spent some time talking about Coulomb's law and the size, the charge, that kind of stuff. But it's because of its small size. It's just a proton, the nucleus of an atom. So he said the nucleus was about a centimeter, then the atom would be about a football field, but this is just only the nucleus. So that's what I was referring to.
Proton is smaller than nucleus, right?
Proton, yeah, proton is the smallest nucleus you can have, but you know the charge is +1, so nucleus is like 10 to the 4th times smaller than the atom. So it's,
And how you would attract too many.
it's too unstable because it's high charge. High charge to size ratio. But I don't know if this clicked. If it doesn't click, if something doesn't click, what do? Eventually you're going to have to figure it out. You should figure it out, and you should make a point of figuring it out. So, for example, if this didn't make any sense when we were talking about it last week, then try to make an effort to try to figure it out well before the test. That way, you'll be much better prepared, and it'll make studying a lot easier for the test rather than trying to figure it out the night before the test or just not even figuring it out at all.
When does hydrolysis take place?
What?
When does hydrolysis take place?
When does hydrolysis take place? Hydrolysis takes place always. This is what happens here.
What's
Hydrolysis.
the definition of hydrolysis?
Hydrolysis is just reaction with water. And so water is present because when we have the acid, these are all aqueous. Even though it's not written here, these are all aqueous. And the same thing with all the bases. These are all aqueous. So when we have a water solution of an acid, it's not just acid, it's acid plus water, but water is not a neutral player. Water can act either as an acid or a base. So when we have acid and water, that's actually acid and base. And so hydrolysis takes place here. It takes place to different extents. The strong acids, we expect 100% hydrolysis or ionization. And then for the weak acids, we expect less than 100%. And the weaker it is, the smaller the hydrolysis. In water. And so what defines the strong acids hydrolyze or ionize in water 100%, whereas weak acids partially ionize, partially hydrolyze in water. So when we compare, let's say, something like nitric acid with something like chlorous acid is a weak acid. And so it's not going to hydrolyze to the same extent. Or form hydronium and chlorate. This one, the major species, is likely to be this, molecules. These would be the minor species here. So it doesn't conduct electricity as well as compared to nitric acid. In nitric acid, the major species are the ions here. Like this is the hydrolysis, but we often do this for shorthand purposes. What we'll do is we'll just say HClO2 dissociates into H plus AQ. The H plus always has an asterisk. Why? H plus is going to have an asterisk because it doesn't exist in water. When we see H plus, we think H3O plus. H plus alone is not going to exist in water. Why? Because it has too high of a charge to size ratio. It's tiny. Tiny size. The charge is not so high. The charge is only +1. The problem is it's concentrated in a tiny volume, in a minuscule volume.
So strong acids, they have they have all major, maybe like one kind of what's it called? There are major and minor ions in a solution. Is that what you're saying?
No, I'm saying that these, if you have 100%, that means there's nothing left over here. It's 100% forward. That is, all the nitric acid molecules react with water, leaving none left. If all of them react with water, there are none left. And so that means all we're left with is this. There are no minor species.
So strong acids have major species, or only one kind of species.
The ions.
And weak acids have major and minor species.
Yeah, and the major species is the molecule, the weak acid. So there's going to be some ratio. The stronger the weak acid, the more hydronium. The weaker the weak acid, the less hydronium. We can easily measure this by measuring something called the pH. The pH is proportional. I shouldn't say proportional. The pH is related to how much hydronium you have. The more hydronium, the lower the pH. And so if we increase the hydronium, we end up decreasing the pH. This is what we call the hydronium concentration. If I put square brackets around this, this refers to the concentration. So the higher the concentration of hydronium, the lower the pH. And so what we see is all these have, the strong acids will have the same pH except for sulfuric acid. But these weak acids, the pH increases. So like trichloroacetic acid will have a lower pH, but it has a higher pH than this. So let's say if I have 0.1 molar concentration, that is 0.1 moles dissolved in a liter. That's what we call molar concentration. Then these are all have a pH of 0 or 1. Actually, no, pH of 1. Sorry. And so all these have a pH of 1, but these, the pH will increase. So we start off with a pH of 2 because it's a lot weaker, and then it just increases as we go weaker and weaker. So it's related.
So hydrogen ion has how much percentage of hydrogen?
I'm sorry?
Percentage on hydrogen?
It depends on the concentration. The more concentrated, the lower the pH
Okay.
is. We'll talk about pH later. But we'll see, the pH is going to increase as we get weaker and weaker. And an increasing pH means it's a weaker acid, which doesn't give as much hydronium, which causes the pH to increase. So it's inversely proportional. Inversely proportional. Not only that, it's power function, so it's nonlinear.
If you were asked, for example, to give the, what's it called, conjugated hydroxide for the hydroxide ion, you can go either way. So what would you do?
You look at what you react it with.
Okay.
We have a specific way we analyze these. We'll talk about that in a minute. But just following up on the stuff. What do you do if you don't understand something? Or you miss? It's okay to miss. You can miss like maybe 10%, let's say. It depends on the test. Some tests just to tell you the difference. Most of the tests I had at UCLA didn't have that many questions. I had how many questions on the last exam? Almost 50 questions, something like that. And what that does is it brings the point value of each question down low. At UCLA, like a lot of exams I had 4 questions. 4 questions. Each question was worth 25 points. So if you miss that material, you might have lost 25 points. And so it's really important not to miss anything in case it turns out it's a high point value question. And so the strategy used to study is a little different. Here, I figure if you miss like 10%, you can still get an A. But there, if you miss 10% and that 10% was one of the high point value questions, then you're kind of screwed. And so it's a different strategy for studying. So how do you, if you miss something or you don't understand, well, first, try not to miss something. So if you're at, let's say, UC, how you try not to miss anything, especially since the lectures aren't recorded. Most of the lectures aren't recorded there. You try to compare your notes. So you compare your notes with your friends in class. And so that's one thing, to make sure that, maybe they caught something that you missed, or maybe they missed something that you caught, and so you would do that. And then before the test, you want to make sure you understand everything. This is, because I transferred in, but a lot of people that transferred in with me didn't survive. They didn't survive. They were. Have you heard of something called AP, academic probation? They got on academic probation their first quarter because their GPA slipped below a certain level. And then I think it was 2 quarters of academic probation. There were 2 quarters, my roommate was one of them, 2 quarters of academic probation, and then the 3rd quarter, they were STD. Have you heard of STD? STD is subject to dismissal. So if he couldn't bring up his GPA up to a certain point, then they were going to dismiss him. Well, he couldn't. He got dismissed. And so he was kicked out of UCLA, and they don't hesitate. They'll kick you out if you don't maintain your grades. But I didn't want to be in that same boat either. So you want to think, if the first exam didn't go as well as you might have hoped, then you should make some changes. what types of changes do you make? And there's certain things. And then there are other people who, a lot of people, because they say when you transfer, your GPA drops 1 unit. And so you want to work on, making sure that doesn't happen to you. So if something doesn't make sense, yes, you could ignore it, but, at a UC, it becomes more and more risky to ignore it. Here, okay, you can ignore it. If that didn't make any sense, the proton stuff and the reactivity, then chances are you'll be fine because the point value is not so high. But maybe the professor there might have more. I spent, 10 minutes talking about it. But maybe there 10 minutes last week talking about it. You might not be as lucky. So just be aware of that. And then what you do, if it doesn't make sense, you read it in the book, and then if that doesn't make sense, you read it in other books. If that doesn't make sense, you go online, take a look, and then at UCLA they have teaching assistants, or what they call them, like graduate student assistants or something like that. You can ask them or go to the professor. And the professor is usually available to help you if you need help. Same thing, you could go to office hours. But you want to try to clear things up and not wait until the night before to realize that it doesn't make any sense. So if you're confused and things aren't making sense, then try to get them cleared up. Sooner is better. The other thing is, I know books, people don't like to read so much, but you should read these things and make sure they make sense to you. They go through some stuff here. Let's take a look at this. Base is also hydrolyzed water. So it says the hydroxide ion is the strongest base that can exist in water. These are too strong to exist in water. And the reason is because water can act as an acid. And so if we have any of these, like for example NH2 minus, which is called amide, NH2 minus is too strong. What happens is it attacks water. And NH2 minus is a base. Bases are proton acceptors. So what we form is NH3 plus hydroxide. That's what happened. If we go to, let's say, hydride, hydride is too strong to exist in water. What happens here is, if there's any hydride in water, it reacts with water to form hydrogen gas and hydroxide. All right, if I don't write anything here for the state, it's aqueous. This is just to save time writing. And so technically I should write aqueous here. I should write aqueous here and aqueous here. But what I'm going to do is I'm going to omit aqueous and then just write solid, liquid, gas. And so here water is a liquid, H2 is a gas, and the rest are aqueous. So what it means to be too strong to exist in water is it means that it reacts with water completely. And so this is called base hydrolysis. Base hydrolysis produces hydroxide. The hydroxide is known as base because it has a countering effect to hydronium. So for example, if the hydroxide increases in water, the hydronium decreases. If the hydronium decreases, the pH goes up. As a result, you don't have to learn this yet. And so this is just a side. This isn't going to be on the test yet. This will be on the test after we talk about pH. And so there's a seesaw relationship in water solutions where hydroxide goes up, hydronium goes down. Hydronium goes up, hydroxide goes down. So there's a balance between hydroxide and hydronium in water. So we call one the base, the hydroxide, the other is the acid, the hydronium. And so this is the base. This is the acid. Here. Try to. So all these produce 100% hydroxide. You know, it's not exactly 100%, so just say about 100%. But weak bases produce less hydroxide. And so what we see is something like phosphate will produce a higher percentage. So if we look at phosphate, phosphate's a base and it reacts with water. When it reacts with water, it produces a little bit of hydronium and no, not hydronium. It produces a little bit of hydrogen phosphate, monohydrogen phosphate, and hydroxide. And so for weak bases, this is the major species over here. And these would be the minor species over here. Whereas for strong bases, the minor species doesn't really exist. These would be the major species here, or the only species. So weak bases are less reactive. Weak acids and weak bases are less reactive. Say. And more stable. Whereas strong acids and bases are highly reactive. Yeah, and unstable. In water, this could be with water, but once we have that, then we know. I mean, then we could react it with other, there are other acids and bases other than water, so we'll look at that in more detail next. So what we're going to do right now is we're going to look at metathesis reactions. Try to recognize metathesis reactions. Back up in the supplement. And so it's a little bit tricky, so this is why I talked about this here. We call this hydrogen chloride gas. We call this hydrochloric acid. Hydrochloric acid forms immediately when you mix hydrogen chloride with water. It's very soluble. And so even though I start off with hydrogen chloride gas, it's automatically going to be converted into hydrochloric acid when mixed with water. But what we're doing is we're looking at what we're mixing, what chemicals we're mixing together. And the chemicals that were mixed together is not a bottle of hydrochloric acid. A bottle of hydrochloric acid looks like water. It's just a liquid, and it's colorless, and it's clear, and so it kind of looks like water. It doesn't smell like water, though. But we're not grabbing a bottle of hydrochloric acid. We're getting a tank of hydrogen chloride gas, and you buy this in a cylinder. It's pure hydrogen chloride gas. Since we're buying a tank of hydrogen chloride gas, even though I know when I mix it with water, it's going to form hydrochloric acid, and that's going to result in the ions, I'm just going to leave it as hydrogen chloride gas because that's what we're going to buy and that's what we're going to use for this particular reaction. Does that make sense? So I'm ignoring this intermediate reaction that happens here. And for this particular case, which is more complicated, they made it more complicated, whoever wrote it, because they made it HCl gas. I wish they didn't do that to keep it a little bit easier, but El Camino's known as a more, I don't know, rigorous chemistry curriculum. And so we're going to go this way. So we're going to just leave it because that's what you're going to buy. You're going to go and buy a tank of hydrogen chloride gas. You're not going to go buy a bottle of hydrochloric acid. And so we'll leave it, even though I know in reality when I mix the, or bubble the HCl in water, automatically I'm going to form hydrochloric acid. Okay, so let's go back here. And what we're going to do is we're going to try to figure out what all is happening here. And so in the ionic equation, we're going to see what the major species are that are reacting in this particular reaction. So I have a tank of hydrogen chloride gas, and then I'll just add a tube in here. And so I'll be bubbling the HCl gas in the water. And then there's going to be PB. This is going to be, actually, this is not water. This is a PB C2H3O2 aqueous. So when we do this is what we call the CE. When we do the IE, we're looking at the major species in solution. So let's take a look at the IE. And so what are the major species for hydrogen chloride gas? Those would be hydrogen chloride molecules. And so we have these HCl molecules in these gas bubbles here. But for lead-2 acetate, we know that soluble salts, acetates are all soluble. And so for lead-2 acetate, since it's a strong electrolyte, it breaks up into ions. And the ions it's going to break up into are going to be lead ions and acetate ions. And so in solution here, I have HCl gas bubbles. And then I'm going to have lead ions, like this, and acetate ions. And for every lead ion, I have to have 2 acetates to balance out the charge. So I'll just write 2 acetates in there somewhere. that would be it. So we can come up with the ionic equation up here. Let's do that. Actually, I didn't balance this. Let me balance this first before moving on. How many HCl's do I need here? Well, I have 2 chlorides over here with the lead, and I only have 1 chloride here, so I'm going to need to double this one. If I double this one, then I'm going to need 2 of these acetic acids. For the 2 hydrogens here, the 2 protons, and the 2 acetates here. And so this will be 2 HCl. And then over here, I'm going to have Pb2 plus 2 acetates. I'm going to get rid of the aqueous. So if I don't write a state, it means it's aqueous here. It'll save you a lot of time. All right, what about acetic acid? Is acetic acid a strong electrolyte? In other words, is acetic acid a strong acid, strong base, or a soluble salt? It's a strong base, acetic acid. And so if you're not sure, then what we could do is we could take a look at the acid-base chart. And then we look, is acetic acid one of the 7 strong acids? No. However, it is a weak acid here. So we see acetic acid as weak acid, kind of in the middle. Do we see acetic acid? On the left side are the acids. So on the left side are the acids. On the right side are the bases. And the relationship is dictated by the conjugate relationship. Its conjugate relationship is a seesaw relationship. If one side is strong, the other side's weak. If one side's weak, the other side's strong. And so I look at all these bases, and do I see acetic acid here? No. And so what we say is that acetic acid is just a weak acid. If it's a weak acid, then what does that mean? That means we don't do anything. We ionize only the strong electrolytes. So ionize strong electrolytes only. Leave everything else alone. So acetic acid is a weak acid, therefore we just don't do anything with it. We just leave it as is. Is PbCl2 a soluble salt? No, it's an insoluble salt, so just leave that alone. Okay, in the net ionic equation, we get rid of anything that spectates. That is, anything that's the same on the reactant side and the product side, but none of these are spectators. And so the net ionic equation is the same as the ionic equation because there are no spectators. Everything reacts. So here, what happens is the lead and the chloride will react. I'm going to need 2 of these HCl's. The lead and 2 of the chlorides react, and so we're going to form PbCl2, which is going to precipitate as a solid here. And then the acetate and the H plus react to form acetic acid. And so these would be the products of this reaction. Acetic acid is just aqueous. All right, the next one is aqueous solutions of iron 3 sulfate. So what's the formula for iron 3 sulfate? Okay, iron 3 is Fe, the charge.
But sulfate is SO4.
2 minus, and iron is 3 plus. So the correct formula for iron 3 sulfate would be what?
Fe2 SO4.
Yeah. So we could just drop the 3 down here and drop the 2 down here. That gives us Fe2SO43. And then ammonia.
NH3.
Yeah, NH3. NH4 plus is not called ammonia. NH4 plus is called ammonium. Yeah, ammonia. Both of these are aqueous. So what I'm going to do is I'm not going to write aqueous. I'm just going to just leave it like this. Here. Is this metathesis reaction? Now, metathesis reaction is going to have this pattern like this in most cases. In most cases, it has this pattern, which we call the AB plus CD pattern. AB plus CD. When we have an AB plus CD pattern, then what we do is we switch the anions. And what results is an AD plus CB pattern. And we call this double replacement. When I look at this, I see an AB, but do you see a CD? Do you see a CD? No, yeah, only a C. This is not a CD. So this is not a double replacement, right? Let me put a little asterisk here. They made these, this is number 3, and they made number 3 complicated. We should probably start off with something easier, but I don't know if we can, because we're just at number 3. Not double replacement as written. And so we're going to have to insert another page here. Go down here. Sorry, the order is going to get all mixed up. And so what we're going to do is we're going to call this aqueous ammonia. can participate in double replacement reactions. The way it participates is because NH3AQ is equal to NH3 in water. NH3 we can find on the acid-base chart, and it turns out that this is a weak base. And water can act as a weak acid, or an acid. And what can happen is we can form this. If we think acids, are they proton donors or proton acceptors? Acids. Donors. And bases are proton acceptors. And so what can happen is we form some ammonium and hydroxide. This is uphill because it turns out that this is a acid and this is a base. And so what we're going from is a weak base to a stronger base. Yeah, and then we're going from a weaker acid to a stronger acid. Ammonium is a stronger acid than water. How do I know? Well, it's on the chart. You can take a look at the chart here.
Can we do a replacement now?
I'm sorry?
Can we do a replacement now?
Yeah. Right. So when I look at the acids, I see water here, and I see ammonium up here. Ammonium is a stronger acid than water. And what did I say about going uphill?
It's not driving force.
Yeah, there's no driving force, but it depends on how uphill this is. You know, we have different levels. So the stronger the base, you know, over here we have the weak, weaker. Over here we have the stronger. And the stronger it is, the more severe the climb. What we have to think about is we have to think in terms of a particulate level. At the particulate level, there are a whole bunch of ammonias and a whole bunch of waters. And so down here we have a population of ammonia molecules and water molecules. And just like any other population, even though they're all ammonias, are they exact clones of one another? Yeah, they all have the same structure. They all have the same composition. But the next thing is, do they all move at the exact same speed? Are they like robots in sync? Does every single water molecule move exactly like every other water molecule? What do you think? No. No. And so what we see is they don't all have the same energy. You know, there are some water molecules that are moving faster and some that are moving slower. What we see is same thing with ammonia. They don't all move exactly the same. In fact, what we see is that there's a distribution of energies. And so this is like getting a group of bicyclists. If you have a group of bicyclists, some of them might make it to the top of the hill. But do you think all of them can make it to the top of the hill? No, it depends on the energy. Maybe if the hill were pretty small, they could all make it. Well, maybe not. They could all make all the bicyclists can make it downhill, right? Just roll downhill. But not all the bicyclists can make it uphill. And so what we see is that even though there's no driving force here, a little bit can occur. The downhill direction, this is the downhill direction, is the reverse. The uphill direction, a small number of molecules in this population can make it uphill. And the higher the hill is, the smaller the number is. Well, it turns out for ammonium hydroxide, it's like this. Ammonium and hydroxide. It's something like this. Too steep, there's going to be nobody that can make it up. I mean, if this hill is way up here, there's probably zero. And then if it's not very steep, then a lot more can make it up.
What's the hills symbolic of?
I'm sorry?
So bicyclists are symbolizing these molecules.
Yes.
What's the hill symbolizing?
The hill symbolizing the difference in energy. That is the difference between this. This is weaker, this is stronger. It depends on how strong is. The stronger the strong is, the higher the hill. So it becomes less and less favorable.
So in the situation
So yeah, let me give you an example here. Let's say we're going from here, let's see, ammonia here to hydroxide here. This is an inverted hill. Let's take a look at the acid. Let's say we're going from water, the acid here, to ammonium here. And so if we're going from water here to ammonium here, do you see the climb?
Yes.
We have to climb this high. But let's say we're going from water here to hydrochloric acid up here. Do you see how high we have to climb? That's going to be a lot harder to do than something like water to ammonium. So the hill isn't as big. And so if the hill's like this big, then pretty much nobody's going to make it up. But if the hill's only this big, then maybe more can make it up. And so that's what I'm trying to show with the arrows here. I'm trying to show if the hill's this big, maybe nobody can make it up. But if the hill's this big, maybe a fraction can make it up. In fact, a fraction can make it up. Less than 1% can climb this hill. And so this is like 99% this and about 1% this. And so 1% of the population climbed up the hill. The rest, the remaining 99% decided to stay here. It's easier. But there's always going to be that small group that wants to climb the biggest hill possible. And so for aqueous ammonia, therefore, what we do here is for determining double replacement, what we do is we treat ammonia and water as if it were ammonium hydroxide. Ammonium hydroxide, this is what we call, I'll just put ammonium hydroxide here. The problem with this is the major species here, and this is the minor species here. And so ammonia and water, that's our major species. Ammonium hydroxide is a minor species here. And this is called hydrolysis. Weak bases partially hydrolyze water. So weak bases partially hydrolyze water. Weak bases, we have partial hydrolysis of water. Therefore, we treat ammonia and water as if it were ammonium hydroxide. And so treat ammonia and water like ammonium hydroxide.
And that would be the A, B, C, D.
Yeah, that gives us our A, B, C, D. And so in this
Or
case,
like anything that's we can break apart the water in another molecule.
yeah, CD. I'll just label it CD right there.
Oh, so instead of we don't leave it as we don't leave it as ammonia.
We leave it as ammonium water because on their equations we have to have the major species.
Okay.
And so in this equation, I'm going to leave it as ammonia and water. I'm going to just add the water. Why can I add the water? Because these are all aqueous, and there's plenty of water present in aqueous solutions. However, I'm going to imagine that this is going to react like ammonium and hydroxide. There's enough ammonium and hydroxide present. So if I treat ammonia and water as if it were ammonium hydroxide, I'm going to put this in quotation marks because it's the minor species, not the major species. We want the major species in the reaction up here. And the minor species, we don't usually write in the reactions. We don't write minor species, otherwise things get all messy. There's too much stuff. So what we do is we have iron 3. Now we're going to pair it, not with sulfate, but we're going to pair iron 3 with hydroxide. And now we're going to pair ammonium with sulfate. And so what is the formula for iron 3 hydroxide? FeOH2
Yeah.
or 3?
Because it's
3.
iron.
Yeah. And then ammonium sulfate. What's the formula for ammonium with sulfate?
NH4.
Yeah, NH4 2SO4. We can write it over here, like iron 3 is going to require 3 hydroxides to balance out the charge. And ammonium is just a +1, but sulfate is a -2. So it's going to require 2 ammoniums to balance out the charge. So we have that. Next thing we'd look at is is iron 3 hydroxide soluble or insoluble? Hydroxides are all insoluble except for
Group 1.
group 1,
Ammonium.
ammonium,
Strontium, barium.
yeah, calcium, strontium, barium.
I guess we're good.
Yeah, we're good. This is going to precipitate. If this precipitates, that's driving force. That's all we need, is this one. How about ammonium sulfate? All ammonium salts are soluble. And so this does not precipitate. Does ammonium sulfate decompose into a gas? No, salts aren't normally gases, and this one doesn't decompose. So this one's not a driving force. But all we need is one, and we have it here. So we have driving force for reaction. It's the precipitation of iron 3 sulfate. That's our driving force. If we have driving force, let's go ahead and balance it. How do we balance this? The way we balance this is like this. How many hydroxides do we need? Okay, actually, it depends. We have 2 irons here, and I have 1 iron here, so how do I change this? I need to multiply this one by 2. If I multiply that by 2, then how many hydroxides do I have total?
6.
6. How many hydroxides do I have from ammonia and water? Only 1. And so do you know what I need to do? I need to multiply everything by 6. So I have to have 6 ammonias and 6 waters. 6 ammonias and 6 waters will yield 6 ammonium hydroxides. How many sulfates do I have? 3. So over here I'm going to have to multiply this by 3. That's going to give me 3 sulfates here. And then how many ammoniums do I have over here in ammonium sulfate?
2 and ammonium 6.
6. So that works out here. So everything's balanced now.
So you just go back and forth.
Yeah.
With the pairs.
Right. We just go back and forth until everything gets balanced.
So in the end, it will definitely, I guess, balance each other.
Yeah. In the end, it's going to balance. So the ammonium, if it doesn't, then we made a mistake, and we have to go back and figure out what the mistake was. They don't give us much room in these slides here. I should, next time I'll do it one at a time, individually, to make it more organized. So what we have here is we have 2 beakers. One beaker is going to be labeled iron 3 sulfate. And the other beaker is going to be labeled aqueous ammonia. In the iron 3 sulfate beaker, what do we have present? What are the major species present here? In iron 3 sulfate, does it break apart or does it stay together? Well, let's figure out, is iron 3 sulfate a strong acid? Strong acids break apart. Is it a strong acid? Is it one of the 7 common strong acids you've memorized? No. It's not a strong acid. Is it a strong base? No, it's not a strong base either. It's not a hydroxide, soluble hydroxides, amide, sulfide. Is it a soluble salt? Yes, sulfates are soluble. Except for silver, lead, mercury, calcium, strontium, barium. It's not a weak, sulfate is a weak base, but iron 3 sulfate is a soluble salt. If it's a soluble salt, soluble salts are strong electrolytes. Strong electrolytes break up into the ions. So we get 2 iron 3s and 3 sulfate ions. And like that. And so in the complete equation, we have iron 3 sulfate, aqueous. But in the ionic equation is going to list the major species. The major species will be iron 3 plus ions, aqueous, and 3 sulfate ions, aqueous. Okay, then we had 6 ammonias and 6 waters in the balance. So we got 6 ammonias, and then we have to have 6 waters. We have plenty of water in here. Way more than 6. Now, we know that these 6 ammonias are like this, but we also know that not all the ammonias are moving at exactly the same speed and same energy. What happens is, like, 1 out of the 6 might be much more energetic than the other 5. And so one of these might react with the water. If one of these reacts with the water, then what do we form? We form a little bit of ammonium and hydroxide. And that little bit of ammonium and hydroxide can react. And so if I see this 6 ammonias and 6 waters, then we treat this kind of as 6 ammonium hydroxides, because overall we're going to have a lot of ammonias in here if we're looking at it at the particulate level. But we just need 6 out of this huge population to react in this way. But that would be the minor species still, because the major species will be ammonia. We're going to have a lot more ammonia in there. And so what we're going to do is we're just going to treat it as 6 ammonias and 6 waters. Not ammonium hydroxides, because we're looking at the major species present. Ammonia is a weak base. It's not a strong base. And so we leave it alone. And so in the ionic equation, only ionize the strong electrolytes. Only ionize the strong acids, the strong bases, and the soluble salts. Leave everything else alone. Leave everything else alone. Because those are the strong electrolytes. The weak electrolytes and the non-electrolytes, the major species is just itself. Yeah, and in these equations we just write the major species, because if we have to start writing all the minor species, it's going to get all mixed up. We could write all the minor species too, but we're not. Okay, then we're going to mix these together, and what do we form? We're going to form a precipitate. Of iron 3 hydroxide. And we're going to form a solution of ammonium sulfate. And so this is our ammonium sulfate aqueous here. And so in the conventional or the complete equation, we form 2 FeOH 3 solids plus, how many ammonium sulfates? 6. There's 3 ammonium sulfates. All right, so we're going to try to figure out what the major species are here. If I have an iron 3 hydroxide solid, what's the major species? Or in other words, let's figure out, is iron 3 hydroxide a strong acid? No. Is it a strong base?
No.
Is it a soluble salt?
Yes.
It's a soluble salt, yes.
No. Is it strong acid?
It's not a strong acid. It's not a strong base. It's what we call a precipitate. Precipitates are insoluble salts. Hydroxides are all soluble, hydroxides are all insoluble except for which ones?
Barium, calcium, strontium.
Yeah, group 1, ammonium, and barium, calcium, strontium. We call the soluble hydroxides strong bases. This is weak, and so we just leave it alone. It's an insoluble salt. Insoluble salts we leave as is. Are ammonium salts soluble or insoluble?
They're soluble.
Yeah, and so soluble salts we ionize. And so what does ammonium sulfate ionize into? How many ammonium ions? 6 ammoniums. And how many sulfates? 3 sulfates. So we break it apart into ions. And when we break it apart, we just have to make sure we don't lose any. And so that's what we end up here. So up here in solution, the major species are going to be ammonium ions and sulfate ions.
Ionization is when it's soluble. After you find the CE, when going to ion,
Mm-hmm.
we find out from the product of it that which ones are soluble, which ones are not. When that's not soluble, for example, the iron in this case, just the way it is, because that's the minor species. And then the one that's soluble will be the major species in the case.
Yeah.
And we'll ionize that one, which means it's breaking the other molecule.
Yeah. And so, yeah, the ionic equation just shows the major species present in solution.
And
So-
the net ion equation is things that cancel out and
Yeah.
what's left.
Right, but nothing cancels out. You see you have iron 3 here, but you have iron 3 hydroxide over here. You have sulfate, actually sulfate cancels out. Do you see the sulfates?
There's a
We have sulfates here, and we have sulfates here. They didn't change. So the sulfate we can cancel out. But the iron we can't. The ammonia we can't, because ammonia and ammonium are 2 different things. And the water we can't, because water and hydroxide are 2 different things. And so then in the net ionic equation, we get rid of the spectators and just look at what's reacting. And so what's reacting is we'll have 2 iron 3s shown here, iron 3 and an iron 3, reacting with 6 ammonias and 6 waters to form 2 iron 3 hydroxides plus 6 ammoniums. This is hard one because aqueous ammonia is complicated in that sense there. Why don't you try this one here? Actually, let's see, 9:45, 10:40. Let's go on a break right now. It's talking too long. Here. We're going to do manganese 2 nitrate and aqueous ammonia solutions are mixed. So write out the complete equation, the ionic equation, net ionic equation. Tell me what the driving force for this reaction. We need a driving force. If there's no driving force, then we just say there's no reaction. But in this particular case, there should be a driving force. So you can tell me what the driving force will be. So give this one a go and then come back to it. So did somebody figure out the formula for manganese 2 nitrate?
Yes.
MnO3 2? MnNO3 2? Okay, like this? That's correct. Manganese is Mn2 plus and nitrate is NO3 minus. So we need 2 nitrates to balance out the charge. And then for ammonia, what's the formula?
NH3. And
Add H. Okay, good. Add H2O. Otherwise, it's not going to be an AB plus CD. And then we don't write this down necessarily, but we pretend that this is going to be reacting with, well, we don't pretend. It's going to react with the minor species. The minor species are going to be, in other words, we treat NH3 H2O as if it behaved NH4OH, right? Ammonium hydroxide. And I'm going to put that in quotation marks because that's the minor species. The major species is ammonia and water, so we'll just leave it as ammonia and water. So keep working on it. So that gives us our AB and CD. And so what does it form? Oh, okay. It forms AD and CB. Did you figure out the products already?
AD with the manganese hydroxide.
Yeah. All right. What's the correct formula?
MN.
Mn. OH2. Good.
And then go to the NO3. NH4.
NH4.
NH4 and the NO3
NH4NO3. That's correct. The manganese 2 hydroxide, that comes from having 2 hydroxides, each -1. And then ammonium is +1, and nitrate's a -1, so this is just 1 to 1. Is it balanced?
No.
No. So you're going to have to balance it next. So we got the manganese 2 with the hydroxide, so that makes manganese 2 hydroxide. And then we have the ammonium with the nitrate, that makes ammonium nitrate here. These are the correct formulas. Someone balance it?
Yes.
Okay, what did you get?
Just put a 2 in front of NH4 NO3.
2 in front of NH4, NO3?
Yes.
No? You have some more, Jason? Yeah.
I'm still figuring out, but I tried that, but it would give it like 8 hydrogens.
And then we'll like a 2 in front of, in the previous one, a 2 in front of NH3
2 in front of NH3,
and 2 in front of H2O.
2 in front of the H2O, which is going to give us 2 NH4OH. So when I balance these, I balance off the NH4OH. So I have 1 manganese, 2 nitrates, 2 nitrates. And then I look over here, 2 ammoniums, and 2 hydroxides, 2 hydroxides. So then it would be balanced. I don't balance it by atoms. I just know that whatever has to be the same. So if this is 2, this is 2, this is 2. What's in the quotation marks really doesn't belong in the equation because the equation is the major species here. That's what we're going to leave here. The major species that we're reacting, that is.
And the driving force would be manganese hydroxide
Uh-huh.
because it's more solid.
Yeah, it forms a solid. So
And the other one would be aqueous, correct?
yes, correct. Formation of solids is called precipitation. So the driving force is precipitation of manganese 2 hydroxide. That's good. This we call the complete or the full formula equation or whatever. Write the ionic equation next for this. So did you figure is manganese 2 nitrate a strong acid? Strong base? Soluble salt?
Yes.
So what do you do?
Mn2 plus.
Mn2 plus?
And you add it to 2NO3.
2NO3?
And then you add it to.
Wait, there's a problem. Just NO3, nitrogen trioxide?
Oh, negative.
Or NO3 minus nitrate?
Minus.
NO3 minus. It's important. If you don't have the minus sign there, then it looks like nitrogen trioxide, which doesn't exist.
Plus 2 ammonia.
Yeah. Plus 2 ammonia
And then
plus
plus 2H2O.
2H2O. Okay, all these are aqueous, but H2O is liquid, so we'll put a L there for liquid. How about manganese 2 hydroxide? Is that a strong, ammonia is not a strong acid, not a strong base, not a soluble salt. Water is not a strong acid, not a strong base, not a soluble salt. So we leave those alone. But how about manganese 2 hydroxide? Do we leave it alone or do we break it apart? Is it a strong acid?
No.
No. Is it a strong base? Is it a soluble salt? It's not. It's an insoluble salt because otherwise we wouldn't get a precipitate. If it were a soluble salt, it would not precipitate. And it being an insoluble salt means it forms a solid. So it's not an acid, not a strong acid, not a strong base, not a soluble salt, so leave it alone. Did you break it apart? If you broke it apart, that would be incorrect.
It is because it's MnOH2.
Yeah, it just stays as a solid. However, ammonium nitrate, is that a strong acid?
Ammonium nitrate?
Yes. No. Strong base? No. Soluble salt?
Yeah.
Yeah. This is soluble. All ammonium salts are soluble, all nitrates are soluble. So what does this break up into?
2NH4
2NH4 plus,
plus NO3, or 2NO3 minus.
yeah, plus 2NO3 minus. We have to make sure we don't lose any ions. So that looks all good. The NIE, we need to see what doesn't react. So what didn't react here? The manganese react? Yes. How about the nitrate? Did the nitrate react?
Yes.
Nitrate didn't react because you see on the right, it's still nitrate. The ammonia react?
No.
Yes.
Rings.
Ammonia and ammonium are two different things. And water did. Yeah. And so the net ionic equation is like this. We don't show the nitrate because those aren't going to participate. It's going to be the manganese is going to react with the ammonia and the water to form manganese hydroxide, manganese 2 hydroxide solid plus 2 ammoniums. Now the charge is not balanced over here. I have a +2 charge. There are nitrates there, but we cancel them out as spectators. But I still have a +2 charge here. The nitrates are around to balance out the charge overall, but you can see the equations are balanced. 1 manganese, 2 nitrogens, 2 nitrogens, 6 plus 4 is 10 hydrogens, And then I have 2 plus 8 is 10 hydrogens, and then a plus 2 total charge on the left and a plus 2 total charge on the right. And so they don't have to be 0. Just the charge on the left has to equal the charge on the right, which in this case it does. It's plus 2, and 2 times plus 1 is plus 2. So this is an example of using aqueous ammonia. Maybe we'll do one more. We can do one more example of using aqueous ammonia. Yeah. Aluminum acetate. What's the formula for the aluminum ion?
Al plus 3.
Al plus 3.
Acetate H and
C2H3O2 negative. And so aluminum acetate will be,
AlC2H3O2.
yeah, good.
And you add that to what we did before.
Yeah, aqueous ammonia would be ammonia and
H3 plus H2O.
plus H2O.
And then you put ammonium hydroxide below it.
Yeah. We'll put it in quotation marks like this, just to help us figure out what the products are. So this will be the aluminum cation with what anion now? Hydroxide. So aluminum hydroxide is what we're going to form. Yeah. AlOH3. Good.
And you're gonna add that to
Ammonium
ammonium.
acetate will be the other product. So ammonium with acetate.
And H4C2H3O2.
Yeah. Ammonium is NH4 plus, and acetate is C2H3O2 minus. So it's going to give us NH. It's a 1-to-1, so ratio. Whereas this was a 1-to-3 ratio. So we have 1 aluminum, we only need 3 hydroxides to balance out that charge.
Balance out the equation, it's a 3 in front of ammonium on the first one. So 3 in front of H2O and a 3 in front of ammonium hydroxide. And on the right, a 3 in front of ammonium and
Okay, good. So that's all balanced. That's good.
And then for the IE,
Mm-hmm. Oh, well, let's get the driving force first, because
driving force is the aluminum hydroxide.
aluminum hydroxide,
And the solid, it's insoluble, so it's solid.
it forms a solid, right? And so we'll call that precipitate. So we're going to precipitate out aluminum hydroxide, which is a driving force. How about ammonium acetate? Does that precipitate?
No.
No. Is that a gas? No.
No. It's aqueous, right?
It's aqueous, right? Okay, go ahead. This is the CE. You already did the IE?
Right.
Yeah, okay, let's go with your IE then.
Al or aluminum 3
Okay,
and plus 3 acetate.
that's good.
And I'll go down some right now. So it's gonna be AL plus
Aluminum 3 plus, or aluminum ion plus.
yeah plus 3 ammonia plus 3 H2O.
Liquids, yeah.
And then with aluminum hydroxide plus 3 ammonia.
Okay. And so the acetate's a spectator, so we can lose those here. And then ionic. And then ion just shows the reacting species here. So that's good.
Where can we do more of this round for practice? It's in the book or?
In the book, and also I'm just looking at the double replacement for right now, and also the supplement. The supplement, I just wanted to throw in an extra aqueous ammonia. Let's go back to the supplement here.
Question.
Uh-huh.
This question.
How did you tell that the acetate was a spectator?
How could you tell the acetate is a spectator is because when I look over here, I have 3 acetates, and over here I have 3 acetates. So when I have it on both sides, it doesn't change. Everything else changed. Over here I have aluminum ion. Over here I don't have aluminum ion. I have aluminum hydroxide. And so we can get rid of the ones that don't change. Some people say ammonia and ammonium should cancel, but they don't, because ammonia and ammonium are 2 different things. Number 4 and number 5 are not double replacement type reactions. Number 6 is.
Do we,
Huh?
the knowledge with the knowledge we have right now, can you solve the 4 and 5?
Not yet. I'll come back to 4 and 5. Let's just look at number 6. I just want to stick with one type of reaction for right now, and then we'll add more in there.
Are all ammonia, what's it called, or the ammonia ones, random nucleases?
If you're reacting with an AB, yes.
Yeah.
If it's an AB, AB plus ammonia and water, yes, then it's metathesis. But there are some other ones that are acid-base that's just ammonia plus a acid, and that. But we'll talk about those later. You'll be able to recognize it based on the pattern. And so we're just looking for AB plus CD patterns for right now. You know, we want to just get good with AB plus CD.
Are those ones easier?
No, this is similar, you know, yeah. All right, you could work with other people on these here. Why don't you just work on these for right now? The rest of the class, and then I'll help you if you need some help. Just let me know if you need help, and I'll swing by and try to help you.